Okay, our next speaker is Jitendra Malik, who's here from Berkeley.
Okay, and can people hear me in the back? Okay, great. Okay, so yeah, I want to start by saying that TED has influenced me throughout my career, and these are three of the main lines of work where my work was very much influenced by TED. First, going back to mid-1980s when I started as an assistant professor at Berkeley, and I was making a transition from a very computer vision-y view to a view of vision inspired by neuroscience and perception. And this is what I'll talk about most today. There's a work from TED's work in the 90s and 2000s on intrinsic images. This inspired work that John Barron and I did. And then I keep following him all along. And now I'm very much into tactile sensing, and there's some recent papers that I've written with Roberto Calandra et al. And this is an active topic for me right now, which is again following in TED's footsteps. But I'll focus on the first line of work. And it's really these two papers, both with Jim Bergen. One, which is a 1985 paper on spatiotemporal energy models. And this essentially tried to think about movement in terms of filters and separable filters and inseparable filters and so forth. It's a beautiful paper. And then there is this work from, I think this was already alluded to by Yair. And there is a paragraph in there which you could say inspired our work, but I'll get to it. But let me first set the problem in a bigger setting. And the bigger setting is really to think about features and filters from the perspective of like 30 years ago. What people thought about them then, and there are lessons from them which are totally relevant today. And I always like to quote history, and this is a quote about remembering history. So those who cannot remember the past are condemned to repeat it. And I think that it's kind of interesting when we think about intellectual history, we sort of have to recognize that the systems we live in are not ones with complete diffusion of ideas. We actually land up with sub-communities, and these three existed in the 80s. There was a neuroscience perception community, and the way I define a community is actually which conferences do you go to and which journals you publish in. Because in your time is short. In 1 year, you're not going to go to 17 conferences. So there lands up being a primary conference and a secondary conference, and there'll never be a third one. And that defines your scientific life, the people you know, the ideas you know, et cetera, et cetera. So there is the neuroscience perception community, which we used to be ARVO, then VSS. There's the computer vision community, which started with CVPR and ICCV. And then there's the machine learning community, formerly known as NIPS, now NeurIPS. And there are very few people who span even two of these communities, and much less three. And TED is one of those. And I think those people play a major role in sort of diffusion of ideas across this. So to understand what I'm going to say, we actually have to go back to what I think was the most significant common strand, which actually has influenced all three of these communities. And all three of these communities are working on a line of work where the basic core scientific finding is from neuroscience. So we can talk about sort of the center surround cells from Kuffler's time, or more importantly, after that, like around 1960, you have the work of Hubel and Wiesel, right? The discovery of orientation selectivity, and then these cells which were responded to edges and bars and so on. And then building up on those ideas, you have the concept of hypercolumns in cortex. And this is taken from the de Valois book. And they, in addition to orientation, they note, you can see from those figures there, these filters corresponding to different widths. And this idea actually came from this Campbell and Robson, and there was a time when people used to talk about spatial frequency in a global sense, and then later on it became local, patchwise. But this is sort of an understanding set of around 1980s. It was very much debated at that time, and the interpretation of these ideas varied a lot across communities because computer vision people were not aware of what the neuroscientists thought about it at that time. They relied on a cartoon view based on what they had read 20 years ago. And this is still the case across communities today. In any area, you'll find that what people in machine learning think about neuroscience is based on what was active in neuroscience 20 years ago, and so on. So at that time, I think a big debate or confusion was this about features versus filters. And this is a subtle point, but it's a very, very important point. So one view is that those cells were feature detectors. They were detected edges or bars. And this was the view which went over to the computer vision community. And there's a backdrop for it from neuroscience. There's papers from the 1950s, what the frog's eye tells the frog's brain, which is this conception of a unit which is on or off, which finds the bug, finds the edge or not. And then there is this evolution which happened in the neuroscience community, which was sort of a softer view that these are more like oriented Gabor filters or Gaussian derivatives and so on. But this view had not penetrated the computer vision community. The computer vision community, if you will, I think it's gone through 4 phases in my view, in terms of our core representations. In that early era, the core representations were always edges, and edges were binary. Either they were there or not there. They were just 1, 0. There is the phase of filters, and I think I will talk about the transition from the edge view to the filter view, in which Ted's work was influential and my own work was in that, trying to make that transition. There is a third phase of orientation histograms and the current phase, which is of multilayer networks. But in my view, they are actually not, there is no discontinuity with deep layer neural networks. These ideas are all pretty continuous. You can understand them a lot based on what computing power you had available at the time. So the edge view was the dominant view at the time when I was doing my PhD. And actually, it goes back to this thesis by Larry Roberts, 1963, which was a thesis at MIT back in, it's the first PhD thesis in computer vision. And there's work from, you can see some of the references there. And it's actually very easy. It was a cartoon view of Hubel and Wiesel, okay? And even people who should know better, like people like David Marr, they sort of subscribed to this. They wanted edges, and they made up the story that we must do 0 crossings because we want edges. And they attributed to it some neuroscience basis. There was really nothing solid behind that. From the computer vision point of view, this was understandable because we just didn't have the compute. I mean, if we are talking about 30 years ago, we have computers which are 1 million times slower. Moore's law, we talk about forwards, but we should really talk about it backwards. So if you are talking about 1980, you're talking about computers which are 100 million times slower than today, practically 1 billion times slower than today. So what can you do? You clearly want to get rid of the pixels. You land up with 1,000 locations where you have edges and you want to work with that. And that dominated the zeitgeist. And then we made up justifications for it. And there's this famous example that I like, which was very influential to me. I wasted many years of my life because I was totally swayed by this, which was that you can throw away the pixels, replace it by lines, then throw away the lines by straight segments. And then I thought, therefore, all we should work on is line drawing interpretation. And that's what my PhD thesis was. And it took me years to figure out that line drawings are not the input, but the output of the system. And once I realized that, and this happened somewhere around the time when I was at Berkeley and I was hanging out with neuroscientists and psychophysicists, that I decided I must change what I did. And then I came across these papers of Ted's, right? This one and this one. And this one I said, okay, I know we can do, there's a paragraph there which is models for texture perception. He sort of critiques the Euler's view. And then although we do not present a full model of texture perception here, and I said, aha, I will do that, okay? So, and the above demonstration indicates that simple filtering processes, blah, blah, blah. Anyway, so I will talk about it for 2 minutes. So This is the classic phenomena from Bela Yulish. It was beautiful findings. To me, it was like an example that it made me change my mind from trying to have mathematical criteria of defining a task to a perceptual criteria which was very repeatable. And so I wrote in that paper, the judgment, how we define what is good at the task is what do humans see as different texture boundaries, which was a fight with computer vision people, but I stood by it, and I think it stood the test of time. And then the model was, now we just, again, the most boring model, which is take the various possible filters one could have, which we know from neuroscience-oriented filters at different scales, different orientations. You convolve, you'll see that those filtered outputs reveal the differences between these different areas. And then we had, and then this paper actually goes into why you need nonlinearities. This is an 89 paper. Then on top of that, you do a second stage of filtering. So I think, I mean, to Yair, I would say I knew this. It didn't need Fefe to say that you knew many layers of convolutions and nonlinearities. It's all there in that paper. So layers of filtering followed by other layers of filtering with, why you need that? Because convolution, if you compose just linear filters, then it's equivalent to one layer. And then what we showed was that we could explain psychophysical phenomena about what textures are easy to segment and what are difficult to segment. And then we had some numbers, and then we plotted them and so on. And somewhere in there is when I got to know Ted, because I'd only read his papers. I was totally an outsider. And I don't know, Ted, if you remember, but somehow where you found me because you were a reviewer for this paper. So Ted was a reviewer for this paper, and he sought me out, and it was a great moment for me because I'd only, I was like a kid. I only knew his papers, and this was like meeting a major figure in the field. And then, of course, we became friends and colleagues and so on and so forth. So my point is, we already knew some things there, okay, which is that we need to not think about, it was, for me, convincing. Instead of edges were the wrong thing, filters were the right thing, and you needed to have multiple filters. We didn't know what to do about how to find these layers of filters later. The first layer, the neuroscientists had already told us, and we could create arguments. But this became, for me, at least for a decade, or maybe 5 years, the theme. And I had multiple students at PhD thesis, which are all about filters for stereopsis and filters for optical flow, and then filters for shape from texture. And Ruth Rosenholz was my PhD student at that time. And of course, that's another influence on TED, but we'll get into that later. And the community as a whole was even started to do recognition. So there's the Schmid and Moore work and so forth. So there was a switch. But of course, it didn't stop with filters. The next switch was orientation histograms, SIFT and HOG, which you can think of as variations on this theme. And then we got back to training these multi-layer networks. So this third community, let's talk about that third community, which is the machine learning community. And their origins go back to McCulloch and Pitts, let's say, Rosenblatt. But I want to point out this paper. So this is the direct link. I said that Hubel and Wiesel's ideas, properly interpreted, okay, they have an influence in neuroscience and perception. They all have a strong influence for computer vision. But this third tradition, the learning tradition, also comes from there. And if you haven't, how many people know this paper? Okay, so that's good. There's a well-educated audience, because I always have to, when I give a talk in a deep learning crowd, 99% of the people don't know this paper. This paper is directly based on Hubel and Wiesel. It has all the layers. It's got everything. It's even got shift invariant stuff, so it's got convolution in there. And by the way, what problem did they apply it to? Digit recognition. Yeah, Jan cites it. Jan cites it. Okay, the difference was he was trying to be more careful about the biology than Jan was. They were trying to do it by some vaguely Hebbian thing, and it didn't work well. And then of course you have the Jan LeCun 1989 paper, which is basically exactly the same year as our Malik and Perona texture segmentation paper. It's also got layers of filters, except he has got multiple layers of filters. And then he, inspired by the same Hubel and Wiesel ideas, but the difference is that he trains them by backpropagation, whereas we designed them. And for 20, 30 years, this was never the dominant approach, but it became the dominant approach once you had enough compute and enough data. So I'll make my final remark there. So, by the way, small points. One is that we actually had, in terms of nonlinearities, we argued for and used half-wave rectification. Jan, same year, had the hyperbolic tangent, which is not so good a nonlinearity. And somewhere in the course of the deep learning revolution, they abandoned that and switched to half-wave rectification, except that they call it ReLU, which is a horrible term. You cannot simultaneously be rectified and linear. ReLU is rectified linear unit. You cannot be rectified and nonlinear. This is like a contradiction in terms, right? Rectification is nonlinear. Okay, fine. We knew then that multiple layers for filters were needed. So it's not the case that deep learning is a revelation in terms of, anybody from the biology knows that, right? And we know that computation requires that. The difference was really about faith in how to train those layers. And I was wrong. And I knew that work at that time. And I thought the backpropagation way was wrong on two grounds. One was from the biology. I mean, there was a paper by Francis Crick from '89 which says backpropagation is not biologically plausible. So scientifically, that made that idea wrong. Then there was the mathematician's view, which is that this is a non-convex problem, and why the hell would we do this when we have all these techniques like kernels and so forth, which is why, so we will be stuck in some bad local minimum. So the mathematician's view and the scientific view both led against having faith in backprop. But the engineer's view was this damn thing works, and it does work. And it works even better when you have more layers and more compute and more parameters. So that is where I was wrong. And 23 years later, when the AlexNet paper came out, I had to accept that I was wrong. I will end there and say thank you, Ted, very much for being a scientific inspiration and a great friend.
Although at MIT, it's ironic to mention the name, I think you should have Frank Rosenblatt in there as well as Fukushima, because I think...
I think I mentioned him in, yeah, of course.
Just for context, even though...
No, I agree. No, I think I did, I did, yeah.
Okay.
Yeah.
The oldest guy in the room.
Yeah. No, I think I mentioned it, maybe you just didn't hear it. Okay.
Davi.
See, the thinking in the, okay, so the question was about line drawings. Do I still think of line drawings as output? Yeah, I think line drawings are a perceptual construct of the mind. So for example, if you think of subjective contours, those are constructed, right? They're not, we should not think of them as being directly in the pixels. What we can extract from the pixels are filters and outputs, and then maybe on top of that and on top of that. And somewhere there is a representation which is accessible to our consciousness, which is the line drawing. So the mistake was to say, first you detect the edges, now you get the perfect line drawing, and you can throw away the pixels. That was the mistake. That was the mistake which was committed by the entire computer vision community and by me. Because I regarded, because image processing was complex, so if you could throw it all away and it was, that reduced representation was complete, then you'll work with that. But that reduced representation is throwing away too much too early, and it should really be regarded as the final result. I mean, like grouping is a final result rather than the initial input.
Okay, I think we need to move to our next speaker. Thank you again, Jitendra. And now we have Giro. Bernd, are you set up?